Okay, hi guys. In the previous lecture, we saw the reaction of alkene with the hydrogen over surface of NiPT/PD, and we saw some examples of the same. So in this lecture also, we'll be continuing off with some of more examples of reaction of the same. So let me continue. We have something like, okay, so now the question is you have to draw all the isomers of C4H10, C4H8, the alkene ones only, and you have to react it with D2 or a surface of nickel, and you have to output X type of products. So you have to give the answer of X. Okay, so if you draw all the isomers of alkene, you'll have this, maybe this, and lastly you can have this. You can also have a cis one. Okay, so if you react D2 over Ni, you will get D here and D here. There is only one chiral compound here or one chiral center here, so it will have only two stereoisomers. Okay, so if you react this over D2Ni, you will get D here and D here. So you can see there is a center of symmetry in this, and there are also chiral compounds, so it would be a meso compound. There could be one of the meso compound, but we'll have to calculate this with the case that the compound is symmetrical with even number of chiral centers. So in that case, we will have 2 to the power n minus 1, 2 minus 1 plus 2 to the power 2 by 2 minus 1. So it is 2 plus 1, 3 isomers in this case. Similarly, this would be the same case, so I am not taking this separately. Okay, this would be the already taken, already considered. Okay, already considered case. Okay, so now we will have something like this over D2Na. We would have D here and D here. Again, it's having one chiral center, so the total number of stereoisomers for this would be 2 again. So again, if we are reacting with D2Na over this compound, we would have something like this. So again, total number of, so is it having any isomers? No, it is not having any isomers, so the answer would be 1 only. Why? Because this is not a chiral center on which D is attached. CSC groups are same attached over here. Similarly, I beg your pardon, this would also be one isomer only, because this compound, this carbon is not chiral. So total number of products would be 7. Okay, okay, so now the question is little reverse and little tricky. So let me come to this question. So we have X number of isomers that are reacting with H2 over a surface of Na to give N-butane. Okay, so how many total number of isomers can be there? Okay, so this is an alkene. This is a hint given to you. Obviously it would be an alkene. So this can be one case. So include all the isomers, right? So we'll be including all the possible isomers. So this can be one of the case, and the geometrical isomer for this could be this one. Okay, so the X in this case would be 3, right? Let us come into the third example, where we have a compound. It is reacting with hydrogen over a surface of platinum. It produces N-hexane. So what all possible isomers are possible for the N? So for N we can have 1 2 3 4 5 6. This one we can have 1 2 3 4 5 1 2 3 4 5 6. This one, it can actually have 2 geometrical isomers, so including itself, and also we can have something like this. It will also have 2, total number of 5. Y is 5. Let us take this example where we react Z with S2 over a surface of nickel. So we'll have 2-methyl butane. So what is the value of Y? So if we have something like this, then 2-methyl butane is something like this. So the possible possibilities can be either this one or this one or this one. Okay, let us see some more example. Here you have something like Z dash, which is reacting with S2 and PT to form neopentane. So I hope you remember the formula of neopentane. Neopentane is nothing but this. So what can be Z dash? Z dash would be 0. The number of Z dash would be 0. Why? There is no double bond or alkene that can produce this neopentane, because it's already having 4 substituted groups. No other substituents can be, no other double bond can be there between any of the substituent. Okay, let me take this example. So with this example I will be introducing some new concept, so pay your kind attention towards this concept. So we have something like this, and if we react it with H2 over a surface of nickel, platinum or palladium, we will get something like, obviously you know the result, it would be OH. Double bond would be replaced by hydrogen atoms. And if you react with palladium carbon, then you will get something like, and this structure, obviously H are attached here. So any difference you are able to observe? So PDC is a selective hydrogenation. Okay, PDC will reduce the alkene selectively, not like the surface of Ni, which will add hydrogen to all the double bonds, whether it is between carbon carbon or whether it is between carbon and another atom. So that kind of segregation the surface of Ni, PT or PD will not take care of, but PDC will take care of it, and it will only have a selective reduce of alkene. So let us actually document this. So PDC is selectively reduces alkenes, and on the other hand nickel, all double bonds are added with, all double bonds are substituted, or are, so all double bonds are being added by H2, or is added with H2. With H2. Okay, so with that explained, let me draw some of the practice problems for it. So if we react it with H2 over Ni, and if we react with H2 over PDC, this is the product form in this case, and in this case this would be the product form. Okay, and in both the cases phenyl ring will not be substituted. I'll tell you the reason why in a short while. Before that, let us look into this example, this, and a double bond here, and substituted with the phenyl group. So we reacted with H2 over PDC, so we will get something like selective reduce, so only this compound we will get. Okay, and obviously it would be racemic mixture. Why? Because this is a chiral center and the compound is not having POS or COS, so the H2 can actually attack from above the plane or below the plane. Okay, so now comes the reason why the phenyl ring will actually not go hydrogenation even on the surface of HI on a Ni, because this requires high temperature, and secondly it requires high pressure. So only in these two extreme conditions it will actually first convert, it will break its aromaticity and will first add one double bond with hydrogen. Again we have to supply it with H2, then it will become single cyclohexene, then it will become cyclohexene. Okay, and one more reason is, means we have to provide 3 mole of hydrogen. So I'm just writing 3 mole directly here without even need to write hydrogen here and here. So we need to provide 3 moles of hydrogen for this intermediates I1 and I2 to form, and we cannot actually isolate I1 and I2 because first step is the redetermining step. So first step is the RDS. Okay, because first step is the rate determining step. Okay, and why is the first step redetermining step? Because obviously the benzene ring has to lose its aromaticity to convert into this compound, okay, which is obviously having less number of resonating structures. Okay, so let us draw an energy graph for the same. If we have this as the energy graph, then you can easily imagine that this much amount of energy or activation energy required for E1 and for E2 to form before the final product is formed. Okay, so with this we end our lecture, and in the next lecture we'll be seeing reaction of alkene with the KMnO4 and with some other reagents as well, and we'll have some quiz of true false question types. So till then, good luck and goodbye.